Good day, dear students. Let us go to our lecture 3 for petroleum chemistry. The contents are as follows: alkyne chemistry, hydrocarbons burn, unsaturated hydrocarbons, that is arenes we will be seeing, polyaromatic hydrocarbons, introduction, source of PAHs, effect of polyaromatic hydrocarbons on health of human body, effect of PAHs on environmental degradation, applications of PAHs. So alkyne chemistry we'll see. You're seeing this molecule here. It's not an alkyne, it is vinyl chloride. From the last lecture I just want to tell about this. This is used as an intermediate for the polymerization of this molecule, resulting in polyvinyl chloride. Vinyl chloride is synthesized from ethylene by chlorination. When you get vinyl chloride, then vinyl chloride can be easily polymerized to polyvinyl chloride. Now alkyne chemistry will see these are also known as acetylene molecules, and these hydrocarbons, they are possessing one triple bond between two carbons. So a single triple bond results in a hydrocarbon molecule with general formula CnH2n-2. So this is the general trend where alkenes are most reactive than alkanes, and alkynes are more reactive than alkenes, so making them the most reactive of the three basic hydrocarbon classes. So the naming of the alkynes includes with "-ine" ending, and this confirms the presence of the triple bond and the official naming convention which is there, as you have already studied in organic 1. Since a little bit background I am giving, this is involved in petroleum chemistry. So the ethane is the smallest molecule of this, and which is traditionally known as acetylene, and is most commonly used method for referring to this molecule. Then ethane, the structure of the ethane you can see, carbon is there, black one are the carbons, and the red balls are the hydrogen. So it is a colorless gas and is exceptionally unstable when it is pure, and it is useful in number of industrial settings. That is, it has many applications, and it is mixed with other components in the solution and can be handled without its degradation. It is very reactive, and acetylene is explosive, and it is highly undesirable in many applications. So the major uses of acetylene that will include that is converting acetylene to ethylene, that is hydrogenation of acetylene. Controlled hydrogenation is done for acetylene to obtain ethylene, and further ethylene, as you have studied previously, is used for the polymerization of ethylene to polyethylene. So as a combustion component in acetylene welding, and as a basis for acrylic acids it is used. So acrylic acids are used in the manufacture of everything from the paint to the plastic, and many adhesives it is used. So in laboratory, acrylic acids has many applications, and variety of chemicals can be synthesized from it. So in general, conversion of acetylene to acrylic acid is supplanted by the conversion of propene, that is safer. Welding accounts for about 20% of acetylene, that uses the combustion of acetylene with oxygen that will produce a flame that is roughly 3300 degrees centigrade, making it hottest burning common fuel available, and third hottest natural chemical burn. So that is done under pressure. So these substances, they ensure that acetylene is absorbed or in solution, and that is only released slowly as a pressure it is released. So this helps ensure safe transport of acetylene gases, because these are explosive, they have to be transported very safely. Then next we come to propane here, that is acetylene molecule. You have studied one hydrogen is removed from either of the carbon, there the CH3 is attached. You can see the red balls are the hydrogens, and the black balls are the carbon. So this is the ball and stick model. It is a very old one, you can say. Propane is a 3-carbon alkyne. It is a colorless gas, and this is a substitute of acetylene, just I told you, in welding, because it can be safely condensed to a liquid form for transporting and storage as well. And propane has also been investigated. It is used as a rocket fuel for spacecraft intended for low Earth orbit. So its main advantage is that, unlike hydrogen, propane remains a liquid without the need for cryogenic storage. So beyond propane, we will see these are generally useful in applications or in organic chemistry, can be used for synthesizing number of complex alkynes or any other molecules. They can be used to synthesize, and more complex molecules, they have properties that differ from small to explosive alkynes. So large alkynes like the contraceptive norethynodrel, that is having a lot of applications in pharmaceutical applications, other medical applications that include antiretroviral medications. It is used, antifungal medications, and for cancer treatment. Then how hydrocarbons they burn? So ideal reaction, that is these hydrocarbons, they are called combustion or burning, that produces water, carbon dioxide, energy. So the following the basis of the equation reactions. So you can see, as the previously we have seen the alkyne, so you can see the alkyne attached to this polyaromatic alcohol ketone, right? So the energy gain from the reaction will be greater, and the energy is put into the reaction. So it is a common knowledge that a spark is needed, that is to burn hydrocarbon. So the spark represents the energy needed, that is to break the carbon-carbon and carbon-hydrogen bonds of the hydrocarbon molecule, as well as the oxygen-oxygen bond of the oxygen molecule. So the typical C bond, it requires 350 kg per mole to break, and the typical CH bond, it requires 413 kg mole, and the oxygen mole bond, it requires about 498 kg per mole. So the energy released from these reactions, it is released when new bonds are formed. So the HO bond of water, it will release 464 kg per mole of energy, and when formed, and C double bond O bonds of CO2, they release about 800 kg per mole when formed. So the net outcome is the release of energy is in the form of heat. So a lot of energy is being release. So oxygen as a limiting factor. So you can see here example of the methane with oxygen when it is burned. Water plus CO2 plus CO plus energy is evolved. So the atmosphere is not pure oxygen, and this will contain number of gases that includes nitrogen 78%, argon, hydrogen, iodine, and other trace compounds are there. So the effect of other compounds is twofold. So they also act to effectively limit the concentration of oxygen rather than 100% oxygen. Reactions that occur under atmospheric conditions, they are subject to only 21% oxygen. So when oxygen is a limiting factor, it is not possible to pair every carbon atom with two oxygen atoms. So during a combustion reaction, some carbon atoms, they end up with only one oxygen atom, and this will produce carbon monoxide, which is highly toxic. Even CO2 is also toxic. So when combustion produces CO, it is referred to as incomplete combustion. So atmospheric contaminants, contamination can come from petroleum refining processes or from the atmosphere itself, and the most common atmospheric contaminant for this purpose of combustion is nitrogen, that is it is form of N2. So N2 will be burned in at high temperature, that is in the presence of oxygen, which leads to to the producing nitrogen oxide and nitrogen dioxide, and this both will represent about 1% of the output of a common hydrocarbon combustion reaction that is under atmospheric condition. So you have methane here plus oxygen plus nitrogen, so you're getting water plus carbon dioxide plus CO plus nitric oxide plus nitrogen dioxide plus energy. So many things are there. When nitrogen is coming in contact with oxygen, so it is bound to produce, apart from water, CO2 and CO, nitric oxide and nitrogen dioxide plus energy. So both nitrogen compounds, they participate in the formation of nitric acid HNO3. So this is a component of the acid rain. The reactions are given below as follows: water you have plus N2, nitrogen plus nitrogen dioxide, it is giving HNO3 plus nitrous acid. Then this nitric acid will form nitric acid plus NO plus water. And when nitrogen oxide it reacts with oxygen and water, it produces nitric acid. So these are the basic components for acid rain. Sour versus sweet, this petroleum, this is determined by sulfur content which is there in the petroleum, that it contains more than 0.5% sulfur. So sulfur, when it is burned during hydrocarbon combustion, it produces sulfur dioxide, so which is a precursor for the manufacture of sulfuric acid or synthesis of sulfuric acid. So like nitric acid, this contributes to acid rain as well. Once again, update on hydrocarbon combustion, it reflects this new contaminant, and reaction not balanced, and H2S is not the only sulfur contaminant. Others it will include COS, carbon disulfide, SO2 and more. Soot and smoke, we'll see. Soot and smoke, both they are referred to as particulate matters that are trapped in gases during combustion. So here I would like to give you a small example of soot and smoke. Suppose a refinery is there. Whatever the process is going on, you will see you will have a chimney there, long chimney. From that gases will come out. Even if you see in the Asian countries in the subcontinent, India, Sri Lanka, Pakistan, Bangladesh, there the traffic vehicle which is there, lot of traffic, from the silencer you will see the smoke coming out, because some vehicles still they don't have catalytic converters, where here in Namibia, in developing world, you will see, or developed countries, there the cars are, all cars are having catalytic converters, so there is no smoke or soot coming out of the vehicle silencer, which is very good. Otherwise it will create a lot of pollution, and it will affect the human health and the wildlife also. So in Asian countries it is more, where it is still developing stage. So that is the smoke coming out of it, and small black particulates you will see coming out of that. That will have carbon. So the visible dark black component of smoke is the carbon that is incompletely burned, rather than forming CO2 that has formed solid carbon compounds, that is amorphous carbon it will be. So these carbon compounds, they are collectively known as soot, and diesel exhausts account for 25% of all smoke and soot in the atmosphere. So this is generally the result of low quality of fuel that is being used, less refined, and this constitutes diesel fuel. Soot in particular, this will contain large amounts of polycyclic aromatic hydrocarbons that are known as mutagens and carcinogens. So carcinogenic they are. So diesel exhaust, here it is considered most carcinogenic of fossil fuels that are being used in transportation. So unsaturated hydrocarbons, so these are the more double bonds, as we have seen before only. Alkenes and double bonds, these are alkynes, they are triple bonds. So these are mixed with alkanes, petroleum, and they contribute to carbon dioxide per bond. So do saturated cycloalkanes. These are cyclic molecules like um, cyclohexane, like and methyl cyclohexane, like that. So containing one or more rings they can have, and these are generally used for the same functions as the non-cyclic alkanes, and though they have additional uses in creating certain molecules that have specialized ring structures where bonds between carbon atoms are an intermediate between single and double bonds. So molecules in this class, they will include the industrial solvent benzene, suppose. So benzene, we will see this is a ring structure, as you know already, C6H6 is its formula. So the structure of the benzene has a double bond character explicitly drawn. Shorthand version, circle is simply drawn in the inside ring. So each carbon in benzene has a single hydrogen attached to it. So the basic properties here of hydrocarbons, benzene, it is a natural component of petroleum. It is colorless, flammable, sweet smelling, liquid at room temperature, and it is a component of gasoline mixtures. As it has high octane number, benzene is highly carcinogenic. So that's why the industries and in the research laboratories also, it is not advisable to use benzene. They have to take special permission for using benzene. So other arenes, benzene is only the stable hydrocarbons. Rings with fewer or more carbon and are not stable and less importance than benzene, like naphthalene, anthracene, phenanthrene. They are there. Those are polyaromatic hydrocarbons. We will see that in the next few minutes. In some cases, the substitution of the carbon atom with another element, that is, if nitrogen is there, it will produce the aromatic structure as well. And there are, of course, no longer hydrocarbons, but they have important applications, and this can be constructed from aromatic hydrocarbons. Pyridine, this is the most common aromatic hydrocarbon. An atom other than carbon, that is nitrogen, is replaced with a single carbon atom. That is, it produces an aromatic molecule, C5H9 into its formula. Pyridine is a common organic molecule that is found in vitamins and various pharmaceuticals, drugs. It is formed, and it is a precursor for synthesis of many other biological compounds. And pyridine, it has vast applications for pharmaceuticals, and any other number of molecules can be synthesized. Like pyridine derivatives are there many, like pyridine to methanol, pyridine carboxaldehyde to carboxaldehyde, right? Pyridine to methanol, pyridine to carboxaldehyde can be converted to pyridine to carbonyl by hydrogenation with the Arene nickel or normal nickel catalyst. Then we will come to the next topic, polyaromatic hydrocarbons. In short, it is known as PAHs. So polyaromatic hydrocarbons, they are ubiquitous environmental pollutants generated during the incomplete combustion of organic materials, suppose coal, oil, petrol, and wood. They are incompletely combusted, then it is bound to this produce. So they are organic compounds which are colorless, white or yellow. There are thousands of compounds which are in different forms. So the emissions from anthropogenic activities, that is, it will predominate, and nevertheless some PHs in environment, that is, they will be originating from the natural sources, that is, open burning, natural losses, or seepage of the petroleum or the coal deposits, and volcanic activities. So major anthropogenic sources of PHs that will include residential heating, coal gasification, liquefying plants, carbon black, coal tar pitch, and asphalt production, coke and aluminum production. even the catalytic cracking towers. That will be related activities in petroleum refineries, which is more, and the motor vehicle exhaust. That is in Asian countries, you will see here it is more developed. So motor vehicle exhaust, some of the vehicles in the Asian countries, just now in few slides I told you, they don't have the catalytic converter. So PHs are found in the ambient air in gas phase and sorbate to aerosols. So some of the examples of the PHs I have given you: linear one, that is anthracene. Then the angular one, you have the dibenzene AH anthracene, right? That is it is having five benzenes attached to it. Then you have the clustered one, four benzenes attached, that is pyrene. So atmospheric partitioning of pHs compounds, that is particulate gas phase, it will influence the phase, the transport in the atmosphere, and in the way they will enter the human body. So the removal of the pHs from the atmosphere by dry and wet deposition processes they will do, that is which will influence strongly by their gases and or particle partitioning. So atmospheric deposition, it is a major source of pHs within the soil. So the major source of pHs is the incomplete combustion of organic material, that is coal, oil and wood, that I told you. And this can be synthesized chemically for industrial purposes, and there are a few commercial uses for many PHs. So we'll see the examples of anthropogenic sources of PHs, that is ranging from large point source, that is already mentioned in complete combustion, such as incinerators or some industrial processes which are involved, like petroleum refining industry. From that also it can come. Then the smaller point sources, they will include dispersed sources such as automotive exhaust, smoke from wood burning stoves, jet aircraft exhaust, and from the smoking of cigarette and cigar smoke, and backyard barbecues. These are more highly places from where the pHs will emerge. So other anthropogenic sources of pHs, that will include petroleum products spill, sewage sludge, in that also tarry or creosote or any other waste materials. Then applications of PAHs, polyaromatic hydrocarbons applications. It has used as intermediaries. They are used in pharmaceutical drugs for the synthesis of pharmaceutical drugs as an intermediate. In agricultural products it is used. In photographic products it is used. Thermosetting plastics it is used. Lubricating materials it is used. And many other chemical industries it is used applications. So some general uses are S-naphthalene, manufacture of pigments, dyes, plastics, pesticides, and pharmaceuticals, as I mentioned. So anthracene, diluent for wood preservatives and for the manufacture of dyes, pigments. Fluoroanthene, manufacture of agrochemicals, dyes and pharmaceuticals. Fluorine, for the manufacture of pharmaceuticals, pigment, dyes, pesticides. Thermoset plastics. Phenanthrene for the manufacture of resin and pesticides. Pyrene for the manufacture of pigments. The nature and anthropogenic sources of polycyclic hydrocarbons we'll see in this diagrammatic review. That is nature, that is natural petroleum. Vegetative decay, when the vegetative decay in the agriculture, if they get destroyed from that. Rare minerals also can be have, and even the plant synthesis can be synthesized from the fires and volcanic eruptions, that is when there is incomplete combustion. Anthropogenic, it can be petroleum spills, pesticides formulation during the synthesis of the pesticides, herbicides or insecticides, when they are synthesizing those type of compounds. So from that formulation also, then the sewage sludge, pH contaminated media. incomplete combustion, that is road dust, it can be vehicles internal combustion, right, as I told you, from the smoke of the vehicle, that is from the silencer. Then jet aircraft, from that incineration, wood burning, cigarette smoke, coke plants, other industries process, and any other miscellaneous burning. Then dispersion of PHs through the air, the terrestrial and aquatic environment. From the land you can see. So photo 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 list is there. Dry deposition from the aircraft, open burning from the vehicles. You can see when the vehicle is going, that can leach into the ground, right? And from the synthesis of the soil and from the industry, it is coming out smoke that will go into the air, and clouds and wet dispersion that can heat up, biodegradation from that, it is going into the ground, then it will get discharged. So the wet deposition from the clouds, runoff, effluents, that will be affecting the aquatic environment, and it will affect and deposit in the fishes also. Dissolved PHs, it will be hampering the bio biosphere, right? Sedimentary bacterial synthesis might come in. Then photooxidation, biodegradation concentration might be there in the aquatic environment more, even in the land also, that will spillage into the soil and going in underneath the ground, affecting the groundwater, surface water also, it will contaminate. Sedimentation concentration, sedimentary bacteria synthesis. So from the oil spills also, it can happen when the ships are transporting the oil containers. When there is a spillage, so that oil spillage, it will contaminate the ocean, the sea. So that will affect the aquatic organisms. Then for the man, that is, it will affect the man also. Ingestion vegetable roots, leaves, if they are not washed properly and used. Then inhalation, that is active smoking, passive smoking air, a person who is a heavy smoker, cigarettes, as we have seen, and the consume of the meat and the fish can have it smoked or grilled or fried or broiled, that might produce more, and that will be retention in the body, and the waste can come out in the form of the urine and the feces. So this is the dispersion of the PHs through the air, through the terrestrial and aquatic environments. Why are pH of concern? Genotoxic, it will be mutagenic, it will be carcinogenic, ubiquitous, constant input or limited or no control of non-point sources from that also, and regional board section. Then how does this pH enter estuary? Combustion of refined petroleum products, as we have seen, from the vehicular traffic, it can be from the industrial emission, from the board, and from the trains also smoke coming out, and from the ferries also, fishing and commercial vessels also, which are transporting. Then natural and intention burning of biomass fuel, fireplaces, like you want to do when it is very cold at home, you burn the wood, then from that also it is coming out in the campfires also, and natural fires, right? Forest fires catching in United States or anywhere, it will occur when the temperature is very high from that, from the volcanic eruptions. Then uncontrolled and accidental input of unburned petroleum and its products, asphalt or lube oil, from that also it is coming. Then the spill of the crude oil in the ocean. Then corrosive treated piers, pillars. Pillars are there when you have a bridge like that. Downward of the pillar might have this PHS, right? And pier piling, this might affect the environment, aquatic environment. As in the coastal area, we see near the ocean there is one bridge, right? So there you can see, if you go on the top bridge, you go to see the ocean side, you know. In Sopokmon we have, so that one. Then 60,000 gallon diesel spill at Sisan, you can see in Sisan Marsh in April 27, 2004. That was a concern for the toxicity depending on the exposure and the dosage of the diesel feed, dispersion, evaporation, and biodegradation. That is photocredit is Kurt Rogers, San Francisco Chronicle. It came.